Okay, good evening everybody. So this afternoon I had the occasion to watch a video which is a debate between my friend good Blue Marble Science and a flat earther called Brian Leake, and Brian and Blue Marble Science were on a channel known by or owned by a Mr. Gonzales. Okay, now it was quite a respectable debate, as far as I could say, although calling it a debate would be somewhat stretching the imagination a little bit, because Bluey didn't get much of a chance to really say what he needed to. He was talked over quite a lot, but nevertheless, it was more respectable than I've heard on some of the other bogus channels like Nathan Oakley, etc. You know, where they're just a complete disaster. Okay, so now the thing about it is that nevertheless it was still rather disturbing, and disturbing because I would have thought that that some of the topics covered were stuff that you would get, you would have learnt when you were roughly 12 or 13 years old. So this is somewhere between primary school and your first year of high school, and it seems to me that that almost everybody would know the basics of motion. Well, clearly I'm wrong about that, and that speaks volumes about how the education system is working. Okay, so let's have a look at motion, and this will be very, very basic. So let's start right at the beginning, and then we'll go through various aspects of motion, and I will deal with circular motion, which is, for instance, an example of that is the Earth spinning. And then I will look at projectile motion and see how that works, and see how gravity plays its part in motion. Okay, and how we get to know that. All right, so let's start right at the beginning. Now, what I'm going to do is I'm going to move the camera across to the board, and then I will talk while the camera's on the board. Pretty similar to that. Okay. All right, so let's start. So motion. I hope you can see that okay. It's not very straight, but the conditions aren't very good over here at the moment. All right, so let's get some of the definitions right first. Okay, so distance. What is distance? So distance is the amount that you would travel, so a measured amount that you would travel to get from one place to another. So I've got depicted over here. These are depictions of 1 meter across each one. So where we're beginning here, we travel 1 meter, 2 meters, 3 meters, 4 meters. Our distance is 4 meters. Okay, so that's what is meant by distance. So the distance, the amount of time that the amount of travel that we've done between where we started and where we finished. Okay, that's a measured distance. In this case, 4 meters. The unit for distance is meters. And by the way, the symbol often used for distance is S. Okay. All right. The next one is displacement. Well, displacement is almost like distance, except there's a small difference. Distance doesn't tell us, first of all, where anything is going. So in other words, it doesn't give us any kind of direction. Displacement, on the other hand, gives us direction. Not only does it give us direction, displacement is where we finish up compared to where we started. For instance, over here we started at 0, 1 meter, 2 meter, 3 meter, 4 meter. Then we've come back 1 meter, come back 2 meters. So our displacement is, from where we started, is only 2 meters. So displacement x equals 2 meters. So again, the unit x for displacement equals 2 units. Okay, let's say for instance we didn't come back, we stopped at the end. 1 meter, 2 meter, 3 meter, 4 meters. We're not coming back, so our displacement is 4 meters. Let's say we come back all the way back to where we started. 1 meter, 2 meter, 3 meter, 4 meter. Back 1 meter, back 2, back 3, back 4. We're back where we started, so our displacement is 0. So that is the difference between distance and displacement. Displacement, again, has direction. Okay, let's have a look at speed. Now there's two here, there's speed and there's also velocities. We'll talk about them. I've only written down speed. Actually, what I'll do is I'll write down velocity over here just to be sure. Okay, velocity. Okay, so speed and velocity, they are different things as well. Okay, so what is speed? Let's have a look at speed. So here we're just depicting 4 meters. Okay, so 4 meters, these 4 meters over here, 4 meters. How long did it take us to do 4 meters? The 4 meters traveled in 2 seconds. So we managed to travel 4 meters in 2 seconds. So 4 meters in 2 seconds. 4 meters divided by 2 seconds. Meters per seconds. 4 over 2 equals 2. That's 2 meters per second. Okay, per meaning divide. Let's have a look up here. If you see times, that's of, per meaning divide, and if you didn't know that, cent means 100. Okay, so per cent means out of 100. 2 meters out of seconds. Okay, per second. 2 meters per second. Okay, next. Time in the SI units is in seconds. So again, we express everything in seconds. The speed of light is expressed in seconds. Okay, so in meters per second. So 3.0 by 10 to the 8 meters per second. Okay, velocity. What's the difference between speed and velocity? Well, remember, displacement tells us where you're going, gives us direction. So velocity is displacement over time. Okay, speed is distance over time. Velocity is displacement over time. Okay, so how fast we're going? What's our average speed? Is the amount of time that we've taken to travel a certain amount of distance. Okay, displacement, how much displacement did we do? Where did we finish up? Over the amount of time that it took to do that. Okay, that's displacement. Okay, now let's have a look at the next one. So acceleration. So acceleration is simply the act of increasing velocity. So the velocity increases. Now velocity can increase uniformly. So in other words, the velocity has a uniform acceleration. Okay, so it gets faster and faster and faster in a uniform kind of way, or it can be in a non-uniform kind of way. So there could be no rhyme or reason to how fast it goes from 1 second to another. It may or may not be predictable, but even if it is, it's not linear. It might be exponential. Okay, or it might be slowing down, for instance. It might be braking. So braking again may not be, doesn't necessarily need to be linear. Okay, so let's have a look at this. So acceleration, meters per second squared. So meters per second per second. In this case, meters per second per second. Okay, so let's have a look. So if we've got uniform velocity, okay, so in other words, it's uniform velocity, the velocity is not changing, that means the acceleration must be zero. Okay, there's no acceleration if you're not changing the velocity. If it's 2 meters after the first second, you're still traveling 2 meters per second after the second second, still 2 meters per second after the third one, still 2 meters per second after the fourth one. You are still traveling 2 meters per second, so therefore you are not accelerating. So therefore acceleration is equal to zero. You would not feel that kind of motion because you are not accelerating. There's nothing kind of pushing you back or pushing you forward if you're decelerating or accelerating. Okay, you're moving in a constant velocity. This is what's happened when the Earth turns. Okay, it doesn't go faster and slower day to day. You don't get some days where it's going 26, where it takes 26 hours to go around once, or some days when it takes 24 or 23 hours to go once. It always goes around about nearly 24 hours to go around once. Okay, so therefore you won't feel it because acceleration is zero. So let's have a look over here, okay, at this acceleration. This is uniform acceleration. So in this case over here, the first second, the velocity is 2 meters per second. The second 4 meters per second. The third second 6 meters per second. Next 8 meters per second. Now, okay, so in the argument that they were having, the constant acceleration was, they were talking about 9 or 10 meters per second. Okay, so I think the argument was how fast would you be going after 3 seconds? And I think there was some confusion between how fast you'd be going, what speed you'd be going, and what distance would you get. So I think there was quite a bit of difference in the understanding there. So sometimes Brian would say that he was interested in the distance, and sometimes he would say that he was interested in the speed, or that you would get. So given that mostly he was talking about the speed, the first second you would have got, if it was the 9, you would have got 9. The second would be 18. The third second would be 27. Okay, so 9 2s are 18, 9 3s are 27. So I know that Blue Marble tried his hardest to get Brian to understand that, and of course Brian was pretty adamant that Blue Marble was wrong, which was kind of silly, because you can clearly see if the acceleration is constant, then it's just simply multiplying it by the time that you're going to take over here. And I think Brian was confused because he kept talking about the inverse square law. Well, this has nothing to do with the inverse square law, of course. How he thought he might apply the inverse square law to this, I have no idea, frankly. Okay. All right, so let's have a look at this again. Velocity is acceleration by time. Let's say the acceleration is constant, and in this case it's 2. For the first second, 2 times 1 is 2. Okay, 2 times 1 is 2. For the second, 2 times 2 is 4. For the third second, 2 times 3 is 6. For the fourth second, 2 times 4 is 8, and so on. Okay, that is if the acceleration is uniform. In other words, it's not an exponential acceleration, and it's not a kind of exponential deceleration. By the way, acceleration can go both ways. So acceleration can accelerate upwards, or it can decelerate like if for instance, if you're braking, okay, so when you're braking, you are decelerating, so you can feel the braking. It's motion that you can feel because you are decelerating, okay, and if you're going away forward, then you can feel the acceleration because you are changing your velocity, okay. All right, your velocity is changing as you're going along, so that means you're accelerating, okay. Although in this case you're doing it at in a uniform way, okay. In other words, the same amount of acceleration second by second by second. So for instance, if you wanted to save petrol, this is something you would think about doing in your car. So you put your foot on the accelerator and try to accelerate off in a uniform way. So if you do that, then you are going to save money with gasoline or petrol, however you call it. Okay, so if you can accelerate in a uniform way, you will get much more efficiency out of your fuel and your mechanicals. Okay, let's come back again and do a bit more work on the equations that represent motion. Okay. Okay, folks, so that comes to the end of this video, and what I'm going to do in the future is to cover the other aspects of motion. For instance, circular motion and projectile motion, and we'll have a look at Kepler's laws and most of what Newton's done. Obviously, those flat earthers who think that Newton was an idiot, hopefully that'll change their mind. Okay. Now, again, I'll try to keep the videos reasonably short, so people will watch them to the end, and hopefully some people might actually get something out of it. So if you like these videos, please press the subscribe button, and then the like button and the bell, and that will tell you when I'm about to do another one. Okay, I'll see you next time. Cheers.